Oh, wow. Oh, that's right. Yeah, don't let me forget I've got your exams here, but I'm not going to give them to you until after lecture because I don't want you going through it while I'm talking. But remind me. So how's it going? Is it working?
Yeah, it's working right now.
It's working right now.
It stopped in between for some reason.
Okay. What time is it? I guess in a couple of minutes. I wish they had at least a wireless mouse so I could sort of...
Is it okay if we just focus on the slides? Or?
What's that? Yeah, we just focus on the slides, and I just want to get closer to, yeah. Shall we begin?
Yeah.
So you can focus on the slide and just leave it. Yeah, don't worry about it. Even if I go to the blackboard, I mean, I'll send out notes. So here's the thing. So as I said in that announcement or the email, we've been making comments about RL from day one, over and over and over again. And RL sounds like this really mysterious, difficult, and exciting subject. And what I want to do is take the mystery away. It's really simple. It's completely obvious once you understand the dynamic programming equations. And this is actually, I'm giving a short course. I was supposed to be in Germany next week. That doesn't look like it's going to happen. And this is lecture 1 from that tutorial, and I think it's really good for this audience. Can you close? Yeah. So basically, this way you're thinking about RL, and you'll be ready when we actually dive into it. Maybe, I don't know, the week after next or something. I guess, yeah, or next week probably, yeah. I mean, I don't know, we'll see. Okay, so anyway, again, this is like a lecture for, I mean, but I should mention, you all know Aditya. He's now a postdoc at Stanford, and he's a hero behind a lot of this, so, yeah. Okay, so how does this work? So here's the thing. So there's some advertising, so basically stuff for you to read, and also some exciting stuff coming up. Some background, and basically what reinforcement learning is about. And a lot of this, I'm really making fun of the topic. I think it's a messed up area in many ways. There's brilliant people who've done wonderful work, but there's a conservatism in the field that's really stopping progress, I think. And I'll explain what I mean by that. And which is great for us, because it means that there's so many topics left unexplored for us, so it's a really, really great time for control. And then it turns out, what I'm going to do is, and these are fighting words to many people in reinforcement learning, but it's a fact that these algorithms, almost all of them can be cast as stochastic approximation algorithms. You say that to some people in RL, they get angry, but it's a fact, And so once you understand stochastic approximation, you understand the theory behind all of RL. And again, people have done brilliant work. I'm just saying that a lot of things have been ignored just because of very huge conservatism. There's only one way to think about the problem, and there's many. That's, as I will explain, that's a problem. So I gave a short course at Berkeley, and it's online and helpful, which might help to expand what I'm doing in lecture. So it's basically, I'm going to give those tutorials in this course in a few weeks, pretty much. But those have been popular. And there's a bunch of papers here. So this one is all about these OD models and using them to create bases for value function approximation. This one is Aditya's thesis, but it's fleshed out and to create sort of a short course on reinforcement learning, and that's really going to be our book for the last weeks of the course. And this is high-powered, technical stuff that we won't cover, and beyond the scope of this course. Basically, I won't even get into what these are about. Okay, so advertising. So first of all, be on the lookout this fall because it's going to be a whole semester-long program on reinforcement learning, and it's broadcast in real time, and so you can actually watch and send tweets and ask questions. So you can actually be there, even though it's held in Berkeley. And I'll be giving, I helped organize this monster, and I'll be giving this sort of crash course in August in Berkeley. So this is, I mean, this is going to be a really cool thing. So it's got, you know, big shots in RL and also control trying to come together and fight it out and try to come to some common ground because we have very different views of the world, you know. The RL community and the control community. Even though the foundations grew more in the control community than anywhere else. So back in the 90s, so there's this famous paper of Watkins, and around the same time a famous paper of Sutton on reinforcement learning. And these algorithms didn't have a clear objective even. I'll give you the objective in a moment. And it was actually John Tsitsiklis, a professor who's still at MIT, and his students who created the mathematical foundations of the subject and actually explained what the algorithms were doing. I mean, I'll make that clear. So even though a lot of the early days of this field started in control, for example, John Tsitsiklis left it after those two students. So he just walked away, and the computer science community took it over and did beautiful things with it. I mean, bringing in neural networks and making it work, that's a miracle. I mean, for example, there's some fantastic computer engineering. The science, though, hasn't grown much since the late 90s. Yeah.
For that, or?
Well, I passed this out to you all. This means this actually, if you click this, image,
Okay.
it is a link.
Okay, cool. Yeah.
But you could also just Google that and you'll find it. Yeah. Okay, so background. This is supposed to be comedic, all right? There's some sad parts as well. Okay, go to Wikipedia, and this is what they say. RL is an area of machine learning concerned with how software agents ought to take actions in an environment so as to maximize some notion of cumulative reward. Okay? Now, it's very hard to figure out what that means, you know? If you don't know what RL is, I don't know what you would make of that, all right? But what it is, you know, basically, you would like it to teach a computer to control something, like an airplane or whatever. And then there's a whole list of different types of Q-learning. You'll see there's something that's called off policy and some are on policy. You know, off policy, maybe you're putting some crazy policy, but you're trying to learn the optimal policy. On policy, I'm trying to learn properties of a policy I care about. But you notice I highlighted this. Every one of them advertises being model-free. Model-free, remember that. And so that's part of the religion I'm talking about. If you use a model, even in the slightest way, you're kicked out of the club by most of the community, you know. When in real life, you know a lot about the problem. In particular, it's emphasized that I don't know the cost function or the reward function. I only observe rewards as I'm the software agent going around. I say, ooh, chocolate, you know. And I don't even, I don't even know, what kind of candy bars are out there. I don't know anything. That's awesome that it's possible to come with algorithms that can work without any information. But as control engineers, which is my field, that is not what I want. I want to use every bit of information I have, If it's a robotics problem, I know these robots are made of metal. I know they have moving parts. I know so much about the system. So that obsession has slowed down the field, if you ask me. It's beautiful, I understand it, but there's a mathematical purity that people love. But in terms of applications, it's completely wacko in my mind, to fixate on model free, And so examples that people talk about. So stock trading has been an emphasis forever. So since the 90s, people have gone to Wall Street, consulted, trying to sell RL for stock trading. Autonomous cars, I'll send you all a link. So right after the AlphaGo success, how long has it been now? It's like almost 10 years ago, 8 years ago. It's only 5 years ago. I remember saying it's a hoax. I was so amazed. I couldn't believe my eye. That year, there was an article in Vox or something that said, that predicted that there'll be autonomous cars based on the same principles by 2020. And here's 2020. Nothing has happened since AlphaGo. Nothing at all. I don't think DeepMind has done anything in terms of amazing applications since Go and chess, which are amazing. I mean, incredible success stories. But we'll talk about why that is relatively easy to this, you know. And smart grids, smart buildings, you hear this all the time. So what are we talking about? Again, model free, model free, model free. So you will see these algorithms are so slow. If you tried to use RL, model free, for the stock market, by the time your algorithm converged, the coronavirus would be gone, DuPont would be gone because of all the scandals recently. There'd be a whole new economy. It'd take hundreds of years to converge. So it's bullshit, excuse my language. I'm sorry, Florence and Sergio. It's bullshit to say you can do model-free stock trading. No, I mean, there'll have to be a whole new architecture for reinforcement learning, and it will be based on models. Driving cars, again, model-free, no way. I mean, these algorithms are not fast. I don't think they will be fast. You need a lot of data in order to learn, you know. And managing the grid, forget it. So, you know, this is the paradigm of RL. And I think that the foundations are all really useful, but the model-free thing, I want to get rid of that, and just even though you'll see it works, but I want you to think more broadly. Okay, so it's a baby science. So machine learning is almost mature. I mean, they have algorithms that are so reliable for face recognition, you know, and all sorts of other applications. It's amazing. And it's because it's a very controlled environment. You know, I can get tons and tons and tons of data, and then I set up classification as an optimization problem. And optimization theory has progressed so much because of the value of machine learning. It's unbelievable. So there was a revolution in the 90s in communication where you went from 0 to, you know, to your cell phone in 10 years. I mean, unbelievable science was created in a span of 10 years. The same is true of optimization. All right? For RL, almost nothing. There's just nothing like the revolution. And so it's awesome. It means it's a starting point. You know, this could be the beginning of another decade of revolution. And that's why I'm saying you just have to not think about the way people think today. You're going to have to think more broadly. Okay, so here's the big propaganda. So the irony is that this was an obsession in the controls community way before the computer science community. You know, so back in the 60s, 70s, 80s, there was an obsession with model-free, that you could slap a learning system, you know, software agent on an airplane, and it would learn to self-tune and control itself. And one example is an MIT rule, which was to tune a PID controller to control this high-speed airplane. And look at this. So it worked perfectly after the first 65 flights. You know, accurate operator knowledge of aerodynamic characteristics not needed, model-free. And somewhere here it says that the plane was so good that the pilots could do sightseeing. You know, yeah. So this was, you know, this created a lot of hype. You can imagine. You know, and but there were some problems. You know, sometimes the gains changed strangely because of disturbances. There was some bursting of parameter estimates because there were some parameters in this thing. All of these RL algorithms have parameters you're estimating of some sort, like weights in a neural network, example of parameters. And there's some lack of robustness. So you have integral wind-up could be a problem. And so, those problems became pretty bad. And I hate to say this so callously, but, it crashed and the pilot died. And that was it. Yeah.
So if you have a time varying system, right, with adaptive controllers, you can probably get only like a UUV result, right? You can't get asymptotic results, right?
Oh, sure. I mean, what the hell is asymptotics? That's like talking like an economist, that we're going to converge at some equilibrium. Yeah. Oh, no kidding. No, this falls right into the course, like a stochastic control problem. We try a minimum variance sort of thing. We would have, some ergodic cost. We're trying to keep the thing level and all of that. But this was devastating to RL. I think RL, not RL, to adaptive control. I don't think adaptive control ever recovered. And so adaptive control was like, and so, there was a lot of work on robust adaptive control, and it was used in very limited ways in cars, for example, for certain, I can give examples later, but, and paper manufacturing. Carl Astrom did a lot of work there where it was successful because, obviously the burstiness and all that, you lose some paper, but it's not the end of the world. But no more on planes like this. That's it, gone, And so one thing exciting when I was organizing this workshop with the people from Berkeley is that the oral community does not know about this, And so I got to educate the people I was, organizing this conference with and tell them, model-free, created disasters and really hurt the reputation of the control community.
What changed between the first 65 flights and this flight? Like what did the system not really account for?
Oh my God, who knows, Yeah. There is a big report here you can read. But no.
Like the rundown of like how did it crash and burn?
Oh yeah, it's a horrible description of how it, these parameters,
in some region it hadn't explored or something?
Oh, nothing like that. Oh God, no. Nothing. Can you imagine if we were that lucky? See, we can't define what it means to be enough exploration. Here you've got 5 parameters. What is it? You'd have to define your terms. What does it mean? Yeah. No. It's the fact is that the parameters would burst, and it wasn't a big deal 65 times. 66.
When you say burst,
oh, the parameters blow up and come down, and there's some projection or something to keep them from blowing up forever.
Saturating.
Yeah, they have some, we project it, so it's saturation. But nobody will really ever know all that. It's just, nobody can analyze these complex systems. You see, when we do classical control, now how do you control an airplane? There's all sorts, it's a distributed control architecture. You put in all sorts of local control loops on the ailerons, flaps, whatever, elevators, to make them look linear, because they're highly nonlinear systems. You've got that. And then that justifies a central controller based on robust control, linear techniques, where you have a lot of intuition about phase margins and gain margin, all that. When you just slap on a learning system, there's no longer any theory. There's no gain margins, phase margins, nothing. And so all the intuition from classical control is out the window. So I think you would need, RL is an emerging science evolving aside. You need tools for answering the question you're asking. We have no tools right now. And we might discuss some potential tools in the future, but they don't exist today. Okay, so now what I'm going to do is explain to you what reinforcement learning is. Basically I can tell you everything I know almost in 5 slides. Give you the whole field almost, with the exception of a few little tweaks. Okay, so this is a famous hill climbing problem that's on the AI Gym. This is gym.openai.com. And this is really a wonderful resource. You can go on and be in this artificial environment where, there's some randomness. They don't give you a model. You just get to tell this car left, right, or neutral, and it will respond in some random way to your commands. And the goal is to get to the top of the hill and stay there. Okay. Now, very, very simple control problem you can imagine. Although there's not a lot of actuation, so if you just say, oh, I'm just going to go flat out full speed to the right, you'll get there, and you'll stop. So an optimal solution is going to go up for a bit, and then swing over, and then swing back, and swing over, and then it's under-actuated. It's not enough torque to get up there in one shot. And so there's some really pretty things here. So the state here, again, understand the physics of the problem. Just to say what the state is, I need a model. So position, velocity of the model, and UK is the force. Choosing the state, requires a lot of understanding of the problem. Okay, and so we're going to look at this finite horizon optimal control problem, where basically we're trying to minimize the cost, and this could be just one. So we're trying to minimize the time to get to the top of the hill. So you could just be identically one. And again, tau is the first time to reach the hill. That's it. And so there's a dynamic programming equation. This is just like we've seen before. I might have to, at the top of the hill, my cost is 0, and I stay there forever. Okay, so we know that J star at the top of the hill is 0. Okay, and that's how we get this dynamic programming equation. Okay, so it's a cost one step plus the remaining cost to go. So that's something you all should be able to derive. Think about it. And so, how long did it take you to do this? To get that plot? You hacked away at this since last summer?
Yeah.
So there's something called ZapQ learning we'll talk about, which is brand new for neural networks. As of this guy, and maybe this guy. This is the value function obtained with neural networks, where that's position, that's velocity. And that's that. And so if you know the value function and you know the model, then you can just perform this minimization. The minimizer gives you the optimal input as a function of the state. Okay? Just like we've seen for stochastic problems. All right? So whenever you have a Bellman equation, the minimizer is the optimal input for a given state. So it gives you a state feedback policy. All right. Now, here is the brilliant idea. So Watkins, in '89, something like that. Oh, his thesis was '87, I believe. He said, let's call this the Q function, and Q stands for quality or something like that. I always joked it was the first name of his girlfriend or something, but because Q learning. So he decided to learn this. So why? Number one, if I know Q, I know the optimal policy. Because this is what I care about. I care about this. And this, there's a model that creates x1 from x0. I'm trying to get rid of that. I don't want, x1's a function of x0 through that model, right? But if I could learn Q star without knowing the model, that would be the dream of RL since the 80s. So first of all, that's an obvious thing to do if that's all you care about, because I want to get the policy. But what was incredibly ingenious is that by trying to learn Q instead of J, you can come up with Monte Carlo learning algorithms to estimate Q really easily. While doing that so for J star without a model is really hard. Okay, so that is the brilliant step. That's what caused the revolution. That's why Q learning is so beautiful. All right, and I'll explain that right now. Okay. All right. That's just saying that again. If we know Q star, then we have this optimal feedback policy, which is just the minimizer. Okay, and this is just another example, and this is due to this guy over there. So, let me just say this. So, Watkins did not try to approximate the Q function. His algorithm is to compute it exactly, and for that you have to have a finite state space and a finite action space. Watkins never tried to do approximate optimal control. He wanted to compute its exactly. So for something with a continuous state space like the hill climbing problem, you have to quantize this state space and use that. All right. The dream is to have a parameterized family of Q functions, and try to optimize of that family some criteria error, minimize the error in this equation. So that until Go Gators, there's almost been no theory for parameterized Q learning until we got into it. There's only one example I can think of for stochastic models. So we'll explain that in the course. But there's been a breakthrough in the last year. Okay. Wait, am I going the wrong way? Yeah. So I'm just going to show you some pictures. So forget what this is. We're looking at one zone of this building. You can hear the nasty fans, and which always makes me wonder, could we really control those fans up and down? People go crazy. What we want to do is try to keep the humidity and temperature in this zone within strict bounds, and forget about all. There's all sorts of inputs. There's supply air and conditioned air coming from the chiller plants, and that it's cooled and all that. Some things that are mixed and outdoor and blah blah blah. So we've got 4 inputs again: the supply air flow rate, outdoor air ratio of outdoor versus indoor, the temperature of the conditioned air, supply air temperature, and then all these state variables. I won't list them all, but the point is that the Q function is a function of all this. So it's a function of 9 variables, states and actions, and they're continuous variables. So you couldn't possibly use Watkins' ideas, So the crazy thing that Naren tried out was to look at a quadratic function of those variables. So I've got a 9-dimensional set of variables here, and let's look at try to approximate the Q function by quadratic in those variables. And quadratic means quadratic plus linear plus a constant. And this is like the hill climbing problem in the sense that it's a finite time horizon, but it's a fixed final time. And I don't know if you remember this, but think back to value iteration, the cost to go and all that stuff. There's a value function for each time step. There's a Q function for each time. And so in order to put this in the context of like the hill climbing problem, I take it back. It's not 9 dimensions, it's 10. What's the 10th state? What is X6? So it's time basically I've got a finite time horizon problem, and the Q function, the value function depends on time, right? The cost, so if it's a 24-hour day, and I'm sitting here at time 12, the cost to go is about 12 more hours, And as I go further along, it's a shorter and shorter time horizon. So there's a value function for each time. A way to avoid that is to make this time. The time at the kth iteration. And then it's a time homogeneous model. And so it's actually a 10 dimensions, not 9. All right. So it took nerve to try this out, and according to this person here, it worked. So again, so you take the Q function, and I made a mistake here to fix these slides, because I've got to increase X to have that one extra. Oh yeah, oh that's right, the previous input is, oh wait a second. Is this correct?
Yeah.
Well then I'm completely wrong. There's X is 1, 2, 3, 4, 5. I mean not 5, 4, but this is 1, 2, 3, 4 as well. So it's actually 8 states, and then the last one is time. So it's nine states, and then the 4 inputs. Shit, I'll have to fix this. Let's go to a test run. So I believe you took a general quadratic.
Yeah.
And so it's basically there's a matrix here which is symmetric, without loss of generality, it's symmetric. And then there's a linear term and this, and each of these constants, that matrix, that vector, that constant, are all linear in theta. It's just hard to write this down. So you write this as a dot product between a parameter and basis functions. That's the standard way to write this down. Again, assume each of these is linear in theta, and see what you end up with something like this. The notation gets ugly, but it blew my mind that this worked. Absolutely, I couldn't believe it. And you'll be the first to ever see a stable algorithm for this, basically. So first, here's some bad results. So basically, you had a simulator. You didn't wait 100 years, 1,000 days of running. So yeah, basically we've got a temperature plot, which has to be in strict bounds, during working hours. You relax the temperature constraints during off hours. Humidity always has to be within bounds. And you can see it didn't work, because this number here is the number of iterations. So we've run the algorithm 1,000 steps. Is it 1,000 days or 1,000?
1,000 iterations.
Is it an hour?
5 minute time step.
5 minute, okay. So after 1,000, after 100,000, the control sucks. Because you can see the zone, it even got worse. So it started out after thousands of iterations of learning, trying to find the best parameter. So we're trying to find the theta star for which the dynamic programming equations are best fit. It did badly after 1,000 steps. After 100,000 steps, it got worse. The temperature is just crazy out of bounds, so it's gone. And the humidity as well. So look, it's in bounds after 1,000 iterations. After 10,000, it's much worse. So fuck it, no RL. But
I think in the 1,000, it's because it was burning a lot of energy.
Okay, it was very expensive.
Yeah, so it's still expensive.
Oh, we should show that too. Yeah. But look what happens. 1 million always seems to be a magic number. So if you go to, so 500,000 still didn't work. It's okay, it gets a little bit better. But after 1 million samples, it's basically perfect. And going to 2.5 million, it's about the same. All right. And it really is weird. Like all the experiments we do, 1 million samples is when it works. But so you can actually do this, and to me it's really gratifying. And this is there's a lot of randomness here, a lot of uncertainty. So it's pretty amazing you can make this work. So so I'm going to tell you what we did, by the end of the semester. I'm not promoting this because we invented it. I'm promoting it because it's the only thing that makes sense. If you have a parameterized family of approximations, there's 2 algorithms that you can use to train it. And one is called GQ, which is terribly slow and nobody ever uses it. And the other one is ZAP, which is like, believe it or not, that's fast. It's weird, It takes a lot of data to learn. Okay. And so I don't think I need to go through all this, do I? It's just that, so Naran over there, it's really cool that it really does capture all the things that a building engineer would care about. it's going to choose a lower value for a conditioned air temperature when the zone is humid. That's obvious, but this is learned in a completely model-free fashion. Just like AlphaGo learned the opening moves of chess, the standard opening moves. It was really reassuring to see that. There's other examples like this. I mean, I can't, I don't think we should go through and explain all of this. These are just cuts of the Q function with certain variables fixed, and looking at just the Q function is a function of airflow rate and outdoor air ratio. Fixing all the other variables and just looking at the dependency on these two. It learns that humid air can be expensive, and So here's an exercise I'm planning to give to the students in Berlin next week, and I'll give it to you now. These are this is the information provided to the algorithm at each time step. What's missing? There is no system here. There's no dynamical system here. I mean, you can come up with some stupid differential equation models. People do it all the time. And it really could be useful for getting insight. So you could take one of these very simple differential equation models, see what the inputs are into that, and so you'd think, maybe I should augment my state in some way. But can any of you think of things that you might add to the state? Things that you would use to make decisions. Forecast of what?
Anything you could put in, like just any exogenous inputs, stuff like that.
Forecast. So just throw it in. So since there's no model here, that's a beautiful thing about model free. Since I never wrote down a Markov model for this, or and the one doesn't exist. You basically just have to throw in features and play around. So you could put in forecasts of occupancy, forecasts of humidity and temperature, and all of that could be really useful because you could get ready for a bad event. And if you